Hello everyone, in this video we will be covering sections 5.1, 5.2. The main idea here is how to use calculus, specifically the concept of antiderivative or integral to find the area of some function. For example, let's say that you wanted to find the area between A, let's say, and B. So you wanted to find this area, okay? And you want to find the exact, precise area. So remember from basic geometry, you can find the area pretty much from geometry. You can find the area of squares, triangles, rectangles, circles, and so forth, which are regular shapes. So everything in this class is going to be based on rectangles. Okay? So now, if you have no idea how to find this, but you still need to approximate something, the laziest way to approximate this, it will be to do a square, or sorry, a rectangle like this. Clearly you can see that the black rectangle is not the exact area, but it's an approximation. Now, if you cut the rectangle in two pieces, and now let's say you have two rectangles, and you add the area of the two rectangles, you can see how the two rectangles may be a better approximation. So if you keep doing this and keep making the area, the base of the rectangles smaller, then your approximation will keep getting better and better. And this is what I mean. Let's say you want the area again from A to B, it's still the same shape. So if instead of, let's say 2, you have 4 rectangles, and you do 1, 2, 3, and 4, you can see the area of these 4 is way more precise than the first one. There's 2. So if you keep making the base smaller and smaller, and this is where the concept of the limit that we use in chapter 2 is going to come in, you can see that the area keeps getting, the approximation keeps getting better and better. Now you can have the rectangles to be outside or to be inside. This is what I mean. Let's say that you want from A to B again. So you could have everything outside instead of inside. But at the end, when you keep making it smaller, you can see that the area keeps getting better and better and better. Okay. So what we're going to do is the following. This is the x-axis. Okay. And you're gonna go from A to B. You're always gonna need the interval where you're going. You're gonna divide this into n intervals, and the distance between each of them is gonna be called delta x. So this will be called x0, this will be called x1, x2, and so forth. The last one is gonna be called xn. And every time the distance is gonna be delta x. Since we want m in intervals, then delta x is going to be the distance between B and A divided by n. Okay, so this is the first thing you need to know. And then notice that the distance between here is always delta x. So that means that xi is going to be equals to A, which is the initial point, plus I times delta x. Okay. For example, you want x2 will be equals to whatever A is plus 2 deltas and so forth. Okay, so this is also going to be important. Okay, So now let's focus on one specific rectangle. So let's say we go from here to here, and we only focus on this rectangle right here. Okay. So we already say that the base is gonna be delta x, but this will be x on xi. So therefore the height is gonna be f of xi. So this will be the height of the rectangle. Okay. So therefore, what should be the area of a rectangle? And this will be in general. Okay. Remember that here the rectangles just keep going, and every time you have delta x for the base, and the height will be the value of the function. Okay. So in general, the area of a single rectangle, okay, or maybe this would make more sense, the area of each rectangle is going to be the base, which is delta x, times the height, which is f of xi, which is the same thing as just f of xi times delta x. This is how it's typically written. So this is going to be the area of each rectangle. So therefore, if you want the total area, since you have n rectangles, okay, so therefore the area is going to be approximately equals to the sum from I equals to 1 to n of f of xi times delta x. So therefore the exact, and this is where calculus things comes in, the exact area is going to be the limit as n goes to infinity of all the sum of all the rectangles, the area of the rectangles. And this is what I mean. As n goes to infinity, the number of rectangles becomes infinite, and it keeps getting closer and closer until you get the exact area. Now it just happens that this is actually equals to also the integral from a to b, which is the antiderivative. So first we want to find the area the long way, just the same way that you find derivatives using limits first, and then the easy way, which you already know, which would be to find the antiderivative. And this is actually called the definite integral, and definite because you have the limits of integration. Okay, so we're going to do two examples the long way, where you have to use limits, and then in section 5.3 you'll be able to do the exact same thing faster or easier using antiderivatives, and it will give you the exact same answer, but you still need to know the long way for the exam. So here it is. All right, let's say you want to find the area between 0 and 4, which in this case will be this green part. So this is what you want to find. Okay, so the first thing you need to identify is that the value for a is 0, the value for b is 4, and from here that means that delta x is going to be 4 minus 0 divided by n, or therefore 4 over n. Okay, then we're gonna need this sums from pre-calculus, or this formula from pre-calculus. So remember the sum from I equals to 1 to n of I is equals to n times n plus 1 over 2. And the sum of from I equals to 1 to n of I squared is equals to n times n plus 1 times 2n plus 1 over 6. Okay, so this is something straight from pre-calculus, or sometimes just college algebra. And we're going to need that. Without the formulas, you cannot find the limit. Also, from what I told you on the last page, xi, remember, is equals to a plus I delta x, but in our case, xi is going to be 0 plus I times 4n, which will just be 4n times I. And obviously here, f of x is just equals to x. So this is the most basic function we can have. So the first thing you should do is always find the area of a general rectangle. Okay. So the area of a general rectangle is going to be, remember, the base, which is delta x times the function, or let me write it one more time, is f of xi times delta x. F of xi, since the function is x, and xi is equals to this, so this is going to be this part, okay? It's going to be 4 over n I, so that's x, times delta x, which is 4 over n. And then you multiply this is 16 over n squared times I. Okay. So therefore, remember that the area is going to be the limit as n goes to infinity of the sum from I equals to 1 to n of the rectangles. Well, let me actually write it out. Where we already find out what each of these is. Remember, this is equals to this. So it will be the sum from I equals to 1 to n, 16 over n squared I. So therefore, this is the limit as n goes to infinity of 16 over n squared, because they don't depend on I, times the sum from I equals to 1 to n of I. Now, this is where we need this. Okay. Therefore, this will be exactly equals to the limit as n goes to infinity of 16 over n squared times, if we use the formula, this is equals to n times n plus 1 over 2. So this is exactly that. And remember, this is one of the most basic limits. All you have to do is look to the degrees. The top is n squared, the bottom is n squared. So you just divide the coefficients. So this is equals to 16 over 2, which is equals to a. And that's the area. Now, this one was to illustrate the point, and this is how we're going to do it. The only reason why I picked the easiest example first is for you to convince yourselves that the area actually works. Notice that this is just a triangle, okay, where the base is 4 and the height is 4. So what is the area of a triangle? Remember, it's 1/2 the base times the height, which is equals to a. So you could have just done this to get the answer. The only issue is that this only works because this was a triangle. This will not work in the previous example, or it's not going to work in the example we're going to do right now. Right, so let's do now another example. Let's say now you want to find the area for this. You have a quadratic equation, so this is the parabola. Remember, this is x squared. And let's say you want to find the area between 0 and 2. Again, there is a faster way to do this in the next section, but for now you have to do it the long way. And we're going to do the exact same thing. First, the value for delta is going to be 2 minus 0 over n, or just 2 over n. And then xi is going to be, again, 0 plus I times delta x which will be just I times 2 over n. And notice that f of xi is going to be xi squared, which in this case it will be I times 2 over n squared, or I squared times 4 over n squared. Okay, so that's very important. So therefore a typical rectangle, the area of a typical rectangle, okay, of a typical rectangle is going to be f of x, which will be 4 over n squared times I squared times delta x, and delta x is equals to just 2 over n. Okay, again, this is f of xi times delta x. Okay, this gives you that, this gives you that. Again, we're using the exact same formula, over that the area is going to be the limit as n goes to infinity of the sum from I equals to 1 to n of f of xi times delta x, which is the limit as n goes to infinity of the sum from I equals to 1 to n of, if you multiply this, 4 times 2 will give you 8 n cubed times I squared. So notice, since the sum is with respect to I, you can take the n out, so this will be the limit as n goes to infinity of a over n cubed times the sum from I equals to 1 to n of I squared. Now this is where you need the formula for I squared, which is right here. So therefore this will be equals to the limit as n goes to infinity of a over n cubed times n plus 1 times 2n plus 1 over 6. That's the value you will get from here. Okay, remember that this from the summation formula is equals to this part. Now here, when you take the limit, you don't have to distribute the whole thing, but you have to be very careful here. On the top, if you were going to distribute, all you care is what is the leading coefficient. So notice that you have n times n is n squared times 2, it will be 2n cubed times a. The top will be an cubed plus something else, which you don't care. And in the bottom, this is 6n cubed, which you do care. So now notice that the degree is the same. So therefore the limit is going to be the ratio of the two things. So therefore the limit will be a over 6 or 4 over 3. And this will be the area. You will see in the next slides that you can find this in an easier way, but you still need to know how to do this. Just like at the beginning in chapter 3, you have to find the derivatives the long way, and then there was an easy way. So this is the long way. Now I'm going to show you the easy way, but you need to know both of them. Okay, now in section 5.3, we're going to go over the fundamental theorem of calculus, which, like the name describes, is very, very important. And there is actually two versions of this. So first, we will look into, obviously, version 1. But before we go there, so recall from section 5.2, which we just did right now, that the area was equals to the limit as n goes to infinity of the sum from I equals to 1 to n of f of xi times delta x. That was the definition. But this was also called the integral from a to b of f of x dx, called the definite integral. Now from section 4.9, remember in section 4.9, I start calling this anti-derivatives. So this is gonna be the easy way to do this. Okay. So the fundamental theorem of calculus, that's what I'm gonna call it. So now let me go to fundamental theorem of calculus part 1, which is the most useful part. The book actually calls this part 2, so I guess for no confusion, let me go with part 2 first. It says the following: if f is continuous in AB, then the integral from a to b of f of x dx is equals to the antiderivative. So f will be the antiderivative. Okay. So it will be f of b minus f of a. So capital F will be the antiderivative. Okay, so this is the theorem. It's going to be very, very, very useful. Okay, so let's see how this works. Let's do the exact same example we did in section 5.2. Okay, so in section 5.2, the question was to find the area between 0 and 2, okay, which is this area where this function is x squared. Okay. So then, therefore, the area now is going to be the integral from a to b of x squared dx, where a, remember, is 0 and b is 2. Okay, so a will be 0 and b will be 2. So this is from 0 to 2. Okay. So what we had to do is find the antiderivative, which we know how to do that from section 4.9. So this will be x cubed over 3. And the limits are from 0 to 2. Whenever you do a definite integral, there is no need for a plus c or the constant. In this case, this is the antiderivative. Okay. So according to the theorem, this should be equals to f of 2 minus f of 0, which in our case, this should be 2 cubed over 3 minus 0 cubed over 3, which is equals to a over 3. Now, this reminds me, we make a small mistake on the last example when we took the limit. So this is a correction because the answer has to be the same. Remember, you have to find the limit as n goes to infinity. This was a n plus 1 times n, and then to n plus 1, and on the bottom I believe we have 6n cubed. So I forgot to multiply the a times 2, so a times 2 is 16. So the limit should have been 16 over 6, which is equals to a over 3. And then it will match with this one. So this is the mistake I did in the last example. So just correction to section 5.2. You'll see what I mean when you go back to that part. Now you can definitely see that this is much easier, and if the function is even more complicated, this is where the fundamental theorem of calculus is very useful. For example, if you wanted to do this problem the long way, let's say you want to find the area for x cubed. So let's say this is x cubed, and you wanted to find the area between 1 and 3. If you want to do using the method from section 5.2, it's going to take you a long time, and you can try if you have time, but instead the area is just going to be the integral from 1 to 3 of x cubed dx. And remember, the antiderivative of x cubed is x to the 4 over 4. And this will go from 1 to 3. So therefore, this will be 3 to the 4 over 4 minus 1 to the 4 over 4, which will be technically 81 over 4 minus 1 over 4, or 80 over 4, or 20, which is a pretty nice number. Notice that this only took like 5 steps. If you do this with limits using this method, it will take you like 25 minutes to do. But if you have time, you should definitely try. So this is the fundamental theorem of calculus, which relates the area to the integral. There is one thing you have to be careful here, so notice that the area can be positive or negative, and this is related to even and odd functions that we talked about before. If you wanted to find the area from, let's say, from 1 to minus 1 to 1, which will be here and here, notice that the area is the same, so therefore when you integrate, they cancel each other out, so the actual area is 0, and the integral will actually give you that. So the integral of x cubed, we already say, was x to the 4 over 4. So you plug the limits of integration, this will give you 1/4 minus 1/4, which is equals to 0, which makes sense. Okay, let's do a few more examples applying the second part of the fundamental theorem of calculus. Let's say now that you want to find the area between 0 to pi over 2 of sine x dx. You don't always have to do a graph anymore, but it's always useful. Remember, the graph for sine looks like this. So therefore, if you want the area between 0 and pi over 2, pi over 2 is actually here. Okay, so this is the area that you want. All you have to do is find the antiderivative. Remember that the antiderivative of sine was minus cosine. Why? Because the derivative of cosine is minus sine, and this is from 0 to pi over 2. So whenever there is a negative sign or a constant, it's better to put it outside. So then this is cosine of pi over 2 minus cosine of 0. And remember that cosine of pi over 2 is equals to 0, but cosine of 0 is 1. So therefore the area is equals to 1. Now what will happen if you take the area from 0 to 2 pi? Okay. Notice that this is positive, this is negative. If you go all the way to 2 pi, let's see what happens. So the antiderivative is not going to change. It's still going to be minus cosine x. The difference is now you're going to go from 0 to 2 pi. And this will be minus 1 times cosine of 2 pi minus cosine of 0. But remember, cosine of 2 pi is 1, and cosine of 0 is also 1. So therefore the answer is 0, which is not surprising from what I told you. This area and these are exactly the same, but this is positive, this is negative, so they cancel each other out, and the answer is 0, so which makes sense. Right, let's try one more like this. What will be the integral from, let's say, 0 to pi over 4 of 1 plus x squared? Now the graph of 1 plus x squared looks like this, which is actually the first graph from the beginning of this video. And what is the integral of 1 plus x squared? Remember, the antiderivative is tangent inverse. and you go from 0 to pi over 4. So this will be tangent inverse of pi over 4 minus tangent inverse of 0. Remember that tangent of pi over 4 is 1, so this will be 1 minus 0. So the whole thing will be just 1. Okay? So this will go from here to pi over 4. So this area will be 1. Okay, so now let's look to the fundamental theorem of calculus part 1. And this part is technically telling you something that is obvious, that the opposite of the derivative is an integral, and the opposite of an integral is a derivative, which is true in calculus. It's not always true in mathematics, but for this class it will be the case. But this is the formal definition. And it says the following: if f is continuous on AB, then the function g of x defined as the integral from a to x of f of t dt, where x is between a and b. Okay, so if this is the case, then this implies that g is also continuous on AB, and g prime exists on A to B. But more importantly, that also means that g prime is technically just equals to f of x. Or in other words, the derivative cancels the integral. Here you have to be careful because technically you have to use the chain rule, and notice that the derivative of x is just 1. So this is technically times 1. You'll see what I mean when I do in the exercises right now. For example, let's say that g of x is defined as the integral from 1 to x of 1 over t minus phi dt. Okay, so therefore g prime is going to be equals to 1 over x minus phi times the derivative of x, which is 1, and that's it. Now technically this is equals to 1 over t 1 minus phi times the derivative of 1, but since the derivative of 1 is a constant, you don't have to worry about this part. So the answer is just 1 over x minus phi. So you can see this is still the same thing, except the derivative cancels the integral. Okay, so notice that how changes if g of x was equals to the integral from 1 over x cubed instead, or 1 over t minus phi dt, then g prime is going to be 1 over x cubed minus phi. So notice how this limit replaces that one, and then it's going to be times the derivative of x cubed, which is going to be 3x squared. So this will be 3x squared over x cubed minus 5. And so that you can see the whole picture, let's say that the integral was defined like this instead. Let's say this is the integral from x to x cubed, or 1 over t minus phi dt. So therefore g prime is going to be the first part, which will be 1 over x cubed minus phi times 3x squared, and then minus, because this is the bottom, 1 over x minus phi times 1. And this is as hard as this first part gets, which as you can see is pretty simple. So the second part is the one you will be using more often, and that's it.